Okay. Now, okay. What do we mean by an ionized gas? That's where we left off. Any ideas? An ion is an atom that's not electrically neutral, meaning it's either gained electrons and become negatively charged or lost electrons and become positively charged. That's what an ion is. Now, gases, when you heat them up or add more energy to them, or maybe expose them to gamma radiation or something, they will ionize. They will lose or gain electrons. Are there any ionized gases in this room? Yay, nay, or what? Make a guess. Any ionized gases in the room? Fluorescent light, you're absolutely right. An incandescent light is a filament that heats up hot enough to shine, to glow. A fluorescent tube is not that. Fluorescent tube, if you go inside there, there's a thing called a ballast, which is a really strong capacitor. Builds up a great potential difference between the two ends of the tube, and the gases go racing back and forth, picking up so much energy they become ions. And then as they fly by the powder, have you ever seen one of these that break and that white powder inside? That white powder is called the phosphorescent material, that when these ions go by, the phosphorescent material jumps up one of the electrons in the outer shell, jumps up a level, and then when it goes by, it loses energy and falls back down. That gives off a photon of light. And that's why we get lights from this. That's why they don't get nearly as hot as an incandescent bulb. Those get really hot, but these you can almost touch after they've been on a while. A light bulb, you don't want to do that. Okay, now the LEDs, they're even more efficient, but we won't get into that. So that's one type of tail, is ionized gases. They may be emitting their own light because they're a lot like this. The other kind of tail is just dust, because as the comet comes closer to the sun, more of the frozen stuff melts and releases some of the dusty stuff. And then the dusty stuff is close enough. This is very precise language, isn't it? The dusty stuff is then reflects light from the sun. So this could produce its own light. This is reflecting light from the sun. So here's a picture of a comet, an actual picture of a comet this time. In your book, there's another one. Okay? Can you tell me which way this is flying? Is it flying this way? No. All this picture tells you is the sun is this way. This could be moving away from the sun. The head, the tail, always points away from the sun, whether it's coming in or going out. The tail is always away from the sun. All this tells you is the sun's down here somewhere. It doesn't tell you which way it's going. It could be going that way or it could be going this way.
How do you know where's the head or the tail?
The head is here. That's the tail. Okay. This is the solid part, and then it's surrounded by a coma of gases, and that's why you see it here, because it's reflecting light from the sun. Those gases are, and the head is too. And here, this could be ionized gas, or it could be dust. It's also reflecting light from the sun.
You see the head is always away from the sun?
No, the head is always pointed toward the sun. The tail points away from the sun. So you can't tell which way this is going. You just know where the sun is. It's here. And it's either going that way or coming this way. All right. If the sun's here and it's moving that way, it's still, this is just pointing toward the sun. Okay. The one in your book is a very pretty picture too. As the comet nears the sun, it grows brighter with the tail always pointing away from the sun. Now, that pretty much fills up comets. There is another table in your text of examples of spacecraft missions to study comets and asteroids. Okay, and you see some new players in these tables. You see US and USSR, but you also see Japan a couple times, European Space Agency again, a couple of times, and then JAXA, okay? And I'm not sure what that is. Anyone know? JAXA. I wonder if that's Japan, America, I don't know. It sounds like a Japanese name, the spacecraft Hayabusa. So I don't know. But then you see U.S. and European space agencies. There's at least 3 European space agencies there. Okay. Now we move on to asteroids. Okay. These pictures are just, I don't know what, they just sort of make up these examples to give you things to practice on, but we haven't done the math for them or have the physics for them, so that's in the front half of the book. So let's move on to asteroids. Where are most asteroids located? Okay, I heard. Between what?
Between the orbits of Mars and Jupiter.
Excellent. Between the orbits of Mars, which is 1.5 astronomical units away, and Jupiter, which is 5 astronomical units away. So there's a lot of space in there. Now, there it is, between the orbits of Mars and Jupiter. Cleverly disguised. Okay, sizes are up to 1,000 kilometers. I think that's probably a diameter. Okay? Varied composition. The inner belt are stony. The outer belt, dark with carbon. What in the world does that mean? Okay? It doesn't say what it just tells about its color. And obviously carbon has been a part of that. So inside is stony, like rocks and stones, and the outer part is dark, like it's been sooty or something. Okay? The others mixed in between are iron and nickel, which would be sort of stony-ish too. Now, we think they were formed from the original solar nebula. Remember, that was the massive gases that made up the sun, and then there were all the explosions sending things out. Here's a theory, and I think it sounds pretty reasonable. There probably should have been another planet in there, but because of the huge size of Jupiter just beyond that, it kept that planet from clumping together and making a planet. So it has all these rocky things there. Now, let's go back to that concept of Jupiter and all of its moons. Where do you think it may have ripped some of those moons from? The asteroid belt. That would be a very good guess. That's probably why it has so many moons. So it ripped a bunch of them off from the asteroid belt. That's my theory anyway. I think I probably read or seen it somewhere else mentioned as well. Okay? Here's what we're talking about here. Here is Mars, 4/10 of the distance to Jupiter. And, no, I'm sorry. 4/10 of the, okay. 4/10 of the distance between the Sun and Jupiter, and the outer part is 6/10 of the difference between Sun and Jupiter. So you could easily imagine if you collected all these together in one location, you may have had enough to form another planet. But this would have been sort of a rocky planet. We would have had another terrestrial planet here, it looks like. Okay. So that's basically what we got. Remember, in here somewhere is Ceres, the dwarf planet. Big enough, major enough, that it's not just a asteroid. Whoa, that's all she wrote, folks. Like 2 paragraphs is all they have in here. All right. Say again? I can't hear. Don't do it or do it.
I'm going to finish the next slide.
Okay, I don't know what time is it. 4:24? We got to go till 5:15. Of course we're going to finish the next slide. Arm or leg or what? No, never mind. No, we won't go there. Okay. All right. I don't want you to answer that question. Okay. All right. There's asteroids. Let's move on to meteors and meteorites, but I think they should say meteoroids. Meteors and meteorites. And here's why. Okay. Now, what a meteoroid is stuff left over from something else. Okay? That's really a good definition of it. This could be stuff left over from a comet. Now, let's think again what a comet is. Remember, it's an icy body that has rocks and stuff in it, a dirty snowball, right? So when it gets close to the sun, it starts melting some of that ice, so some of that dust and rocks and stuff breaks off, okay? And the comet keeps going, and it leaves this trail of dust behind it, right? After a while, that comet's not going to exist anymore. Even if it's not like Schumacher-Levy that crashes into Jupiter, it's going to lose every time it comes by. So they don't come by very frequently, but they leave this trail of debris. Well, that's what meteoroids are. Trails of debris from either comets or asteroids. Now, I don't really see how asteroids leave much of a trail unless they are also icy bodies. They're far enough out there they may be, and if they come out of orbit and come down toward the sun, they will leave remnants as well. That's what a meteoroid is. So when they said the smaller bodies, it said comets, asteroids, and meteorites. Remember when I said that's not the right word? It should be meteoroids, which is remnants from either comets or asteroids. Because what is it? What makes it a meteor? A meteoroid, when it's out there just in space, in the solar system. What makes it a meteor is when it encounters the Earth's atmosphere. It's no longer going to be a meteoroid because it's no longer going to exist after a while. Because that meteoroid, when it enters the Earth's atmosphere, gets pulled to the Earth, then it hits so much friction, the atmosphere, and going at such high rates of speed, it literally burns up. Or almost burns up. So it's a meteor when it enters the Earth's atmosphere. Never going to be a meteoroid again because it's already on its way out. Okay? Now, what do we mean by a meteor shower? Is that when we clean them up? No, that's not what we're talking about. What do we mean by a meteor shower? Okay, remember I said the trail of dust here? So the Earth enters that trail of dust, you see more meteors that night because there's lots more things out there. We're going to see when some of those are going to be happening. Okay? Now, what is a meteorite then? That's the term they used several slides ago. I said, wrong term. What is a meteorite? It's when one of those meteors that enters the Earth's atmosphere doesn't burn up completely and actually strikes the Earth's surface. It's a meteoroid that becomes a meteor as it passes through the Earth's atmosphere, but not all of it burns up. It strikes the Earth's surface. That's what makes a meteorite. Okay? Not very often. Okay? The asteroid that hit in the Siberia that we were talking about earlier, just about 6 or 7 years ago, that was the last one I've heard about. Now, there may have been some other minor ones, and some of them could be hitting in the middle of the Pacific Ocean and no one realizes it's striking the Earth's surface. Some of them, remote areas and people don't realize it yet, but they don't happen frequently. Most of them burn up completely as meteors. Okay. So, the meteorites, they make it long enough to hit the Earth's surface. There are 3 kinds. Iron meteorites, stony meteorites, and stony iron meteorites. So integrate between the two. Now, of the stony meteorites, there's actually 2 types, subtypes, chondrites and achondrites. Now, what in the world does that mean? Well, in your text, when you get it and can read it, and before I get there, let's look at the meteor showers. Here are typically when we have the most meteors in the middle here. Okay? We had one January 3rd. That was one of the more popular ones. It's the Quadrantid name. That's the constellation where it shows up the most. And that was about 1 every 2 minutes. 30 per hour, 1 every 2 minutes, around January 3rd. The next one coming up will be, after this term's over with, the mini term's over with, right at the end of the spring term. That's Aquarid, meaning Aquarius, and that will be May 4th. About 1 every 12 minutes. I'm not sure I'll focus that long, okay? Especially in the middle of the night. So I probably won't notice that. Perseid, this would be in the constellation Perseus on August the 12th, and that's 40 per hour, which would be about 1 every minute and a half. Right? About like that, something like that. Orionid, my favorite constellation, Orion, that would be on October 22nd, and that's about 15 an hour, which would be 1 every 4 minutes. I guess maybe I could focus that long, I'm not sure. It has to be a fairly clear night, too. If it's real cloudy, you'll never see it. Taurids, it actually has 2 of them. Once where the comet came in, and once where it went back out. I don't know which order. November 1st, and again on the 16th. I'm not going to notice those either. 5 per hour, which is once every 12 minutes. Nah, I doubt it. Leonid, then the next day, on November 17th, again, once every 12 minutes. But the big one is Geminid. In the constellation Gemini, on December 12th, you'll see about 1 a minute, 55 per hour. That one would be worth staying up for, if it's a clear night. Okay? And you can figure out where Gemini was. Okay. Maybe your star chart can help. Okay. So, that slide goes with this part here, the meteor showers. Okay. The next slide here shows some of these meteorites that have hit the Earth. And these almost look like they're backward to me. Okay? The A one there that is so dark is a stony meteorite. Okay? The stony one. The smooth black surface that you have was melted by compression in the atmosphere, because when it's coming through and burning up, it's hot. So it compresses that and makes for that shiny surface there. That basically is what they call a glass, like volcanic glass, only this is meteorite glass. The B one here is an iron meteorite. Now, I usually think of the iron as being very dark, where the stony one would be lighter colored. But here's the issue here. It's been cut, polished, and etched with acid. So that's why it looks whitish, because it's been treated a lot. Why didn't they show the picture before they did that? I don't know. But usually the stony ones would be lighter colored and the iron was dark colored. But this has been treated and it came out different. So I don't know why they did it that way, but they did. The one in your book actually is a little bit better that way, but not a lot. The basic rock you see is a little bit darker. Okay. Now, in your text, they have a time-lapsed picture of a meteor shower. This is somewhere out in a very clear sky on a very dark night, and they just left the camera open, and evidently it was very stable. You see a waterfall here that is collecting a lot of light, but these are the various meteorites flying around there. What are the common names we use for that? Yeah, a meteor. When you see it flash across the sky. Gotcha. Second. A shooting star is one name. The other is a falling star. Okay. Those are 2 common names. There was an old song, "Catch a Falling Star and Put It in Your Pocket." That type of thing. I don't remember. Okay, never mind. I'm not that old. Okay. All right. Now, finally we move. Oh yeah, I was going to tell you about the chondrites, okay, and the achondrites. Here's what those are. The stony meteorites, second time there, are further classified into, subdivided into two groups according to their structure. The chondrites and the achondrites. Chondrites have a structure of small spherical lumps of silicate minerals or glass called chondrules. That's where the name chondrites come from. Okay? Held together by a fine-grained cement. The achondrites do not have these chondrules. Okay? That means no chondrules. Have a homogeneous texture more like volcanic rock, such as basalt, built from molten rock. Now, if any of you, I'm making a guess here, I don't know this for sure, but I know that when you're coming out of Birmingham, coming west on 2059, somewhere not too far from Arkadelphia Road there's a huge mound of something. You know what I'm talking about? Does anyone know what that is? Coal? Really? Sure doesn't look very dark. What's that? Yeah, but that's, are you sure it's coal? It looks like coal. Yeah. Okay. You asked what? Oh. She said, oh. Huge. A rock quarry? Okay. Here's what I was guessing it was, and I may be totally wrong, because y'all may know better than I. I was guessing that is slag. Does anyone know what slag is?
The ball of coal, right? After it's burned.
Yes, that's what we're getting at. So that.
It was dark when it first was freshly.
Okay. Well, you see, coal is actually a rock, and that rock has silicates in it. Silicon dioxide, like sand, only it's mixed in with it. And when you burn the coal, like Miss Lewis was talking about, the coal part, the carbon part burns really, really hot, but the silica doesn't. And
That's what gets in your lungs.
that's what?
That's what gets in your lungs. The silica.
Get it in your
The
lungs?
silica get in your lungs.
Lungs, exactly. For silicosis, right? Okay? But these get so hot that the silicates actually either kind of melt or even coming close to vaporizing, but then when they're cool, they form these little spheres. That's what we call slag. And my guess was that was a pile of slag from years and years and years of burning coal. That's what?
It was left from a process.
Left from the process. Okay.
Because that mound wasn't there. It's been there for close before when I started noticing. That's why the roads are bad there, because
Yeah.
you test that area, and they said it would never uphold the freeway. You always have problems in that. You notice when you go through that area, the roads don't erode a lot there because the soil up under it has been dug out and all that been done to those towns.
They're continuing to fix that because it always needs maintenance.
Always need maintenance because they eating up all the rock.
Right.
That's abundant.
It can't hold it, it's not.
Okay. I didn't know all that. That's really interesting to hear.
Dan
But,
Holloman did the research on that.
who did?
Dan Holloman, he was a biologist at Birmingham Southern.
Uh-huh.
He did the rock study of that whole area, and he told them that when he was getting ready to build the freeway, that it would never, you would always have trouble there because of the rock formation.
Is that right?
And he had a cabinet, a closet, with every rock that was in that particular area. He took it and did samples of it.
Uh-huh.
Yeah, it was right across from my office.
Wow.
Yeah.
That's why I thought it was near Arkadelphia, so I was right. Okay. Now, what I was getting at there, what I just described is what happens when you burn coal. Well, let's just imagine that you have these meteorites coming in, burning up in the atmosphere, then some of that silica, that sandy type stuff, melts and then reforms as little spheres, those are the chondrites. Okay? And if it doesn't have those are the achondrites. Now, does anyone know what glass is? I know you know what it is, but what is it actually? Say again? Yes, it was originally crystalline sand that then you heat it very, very hot and then you let it cool very quickly. It lost its crystal nature and that's what makes glass. And when they say volcanic glass or glassy surface, that's the same thing that's happened there. Heated, melted, and then cooled quickly and made a glassy substance. Okay? Do any of y'all follow Game of Thrones? You do? Okay. When they talk about the material they make the swords with, say again?
The dragon glass?
I guess. Don't they give a name to it? I can't remember.
Someone then they can kill it.
Right, and we're going to hit that in the next chapter or two or three chapters. We'll hit that. Obsidian. Is that the name they give it? I haven't seen the show, but I read the books, or at least the first several of them. And obsidian is the name of that. And that's also a glassy material as opposed to a crystalline material. Okay. Game of Thrones is made up. But obsidian is a real material. It doesn't kill dragons. No, never mind. Okay, I don't know if it does or not. Okay. So, let's move to 15.3, which is the origin of the solar system. Okay? Now here, we've been talking about it some. Now they are trying to put it together. Here is the model. We don't know this is what happens, but this is what we thought happened. Remember before it was a star, what do we call it? A protostar. That was a star in formation, a prototype, Well, when the sun was moving from protostar to star, the planets were protoplanets, okay? So this is the model. Stage A, the formation of heavy elements in many of the earlier stars and supernovas. Remember we talked about that when those really big explosions happen, it fuses together heavy elements, okay? So those are beginning to fall out. The concentration in one region of space as dust, gas, and chemical compounds. This is a very poor slide in my mind. That's the stage A. Now this is what they're talking about here. The sun is probably not quite a star yet, so it's still in the protostar stage, and it's been exploding and stuff and sending out in a disk around it these very hot materials, some very heavy materials, and the concentration in one region of space is dust, gas, and chemical compounds. That's what this disk is. There's the sun in the center, or the protosun in the center, and this would become kind of like the protoplanets. Okay? That's stage A. Stage B, I'm sorry. I've never had my picture taken so much. No, I'm just kidding. What's that?
Are you going to miss teaching this class?
I think so. I'm going to teach it one more time in the fall, if it makes in the fall. It usually does. I may wind up teaching in the summer, but sometimes it doesn't make in the summer. So if I do enjoy it, if I'm going to enjoy listening to Science Friday and doing all that kind of stuff too. Yeah. Everybody through with it now? No? Okay. I'm going to also augment a little bit here. Remember when it's a protosun, there's probably a lot of explosions going on, and that's what's sending stuff out here. But what is the sun made mostly of? hydrogen and some helium. So when it blows that lightweight stuff out there, where does it wind up? Out here in the outer rings, the outer planets, the Jupiter, Saturn, Uranus, and Neptune. It blows that light stuff out. The heavier stuff doesn't get blown as far. Those are the terrestrial planets. I'm sorry, I'm pointing to this. It's up here. So this is what is going to make this happen down here. Okay? All ready now? Okay. Can I move on?
Yep.
All right. Stage B, that's here, the formation of large rotating nebula, again, nebular masses of gases. The sun is sort of settled down and may actually be a star now. Up here, it's probably still a prototype. Boy, that's hot. Okay? But the planets around here are still rotating nebula. They're hot because they just came out of explosions from the sun. They may be heavier materials there, but they still are gaseous, okay, nebula, okay? But gravitational contraction happens and they start spinning faster, okay? Because they're going around the sun and that sort of gives them that spinning nature. Now, some things are a little backwards here. It looks like these two are turning this way and these two are turning that way. I think they're going in the same direction. That's just the artist's rendition, okay? The spin rate increases and that pulls them closer and closer together. Most of the mass concentrates in the central protostar, that's here, so it's still a protostar. The remaining material forms these accretion disks, okay? Now, actually, to me, that fits this better than here, but they're saying that's here, okay? The material in the accretion disks begins clumping, so that's what we see happening here. And we think that big old massive Jupiter out here kept that next band from clumping the way the others did. That left it over the asteroid belt. Now, that's what they think probably happened. Okay? Now, I wouldn't be at all surprised if when all this stuff was going on, something ran into Venus here, had a huge collision, and maybe made it turn backwards. And maybe that's why Venus rotates in a backward direction. Doesn't rotate very fast, 243 days to make one spin, so it's going really slowly, but that might account for it. And maybe somewhere way further out there was another collision, and that may be what turned the axis of Uranus almost 90 degrees. That's just a theory. Oh, and one more. This third planet, the third rock from the sun, which is that? Earth. Oh, that's us. Maybe one of those collisions happened there and knocked off a piece of the Earth and made its moon. Because notice, Mercury doesn't have a moon. Venus doesn't have a moon. Earth has a big old moon for its size. And then you have Mars, which is little moons that probably pick up an asteroid or two. Hey, could happen. And we'll see in the next chapter more evidence that might be the case. Okay. Anyone else? Yeah, oh, you still want more. He gets to listening to my stories rather than writing, I think. Okay. You, my wife would tell you, don't listen to his story. He's just making stuff up, you know. Boy, wouldn't it be good to have your books? Or you could print off things off of YouTube video, from the PowerPoints, and you can have all this written out for you. But if you prefer writing it, it's a good way to do it. It makes it yours. Sure, I think you can. Nothing prevents you from doing that. Okay. All right, can I move on? Yay? All right. The third, stage C, the protostar has finally become a star. The protostar became a sun, the protostar became a star. Should have it one way or the other. The solar ignition flare-up may have blown away all the atmosphere, all four little Mercury, that's why it has no atmosphere, okay? And most of the hydrogen and helium atmosphere is from the inner planets, leaving the heavier stuff like carbon dioxide for Venus, nitrogen and oxygen for Earth, and just carbon dioxide again for Mars, okay? And then the outer planets got all the lightweight stuff, the helium, hydrogen, and helium. They're way out there. The protoplanets have heated, separating the heavy that fell toward the center, iron and nickel, and the lighter minerals like the silicates on the surface. We'll talk about that in a later chapter too. The larger bodies cooled slower with the stress or question?
No.
Huh?
It's a question.
Question, yeah.
So we don't get our books by next week.
Yeah.
Don't come in and just tell me about
Absolutely. You can always do that in the YouTube video if you want to listen to it again. Okay. Of course you would. Okay. Oh, okay. The heavier materials settling over longer times into the central cores. Okay? And that's why most of our cores are iron and nickel, but they have heavier minerals in there as well. And when you do mining, you run into the heavier stuff like uranium and things like that as well. Okay? So that's been happening, and that gets us to stage C. Now they're basically what we know. Somewhere in all that process, probably some pretty major collisions occurred. Okay. Yeah, I got it. Now, we talk a little bit more about that possible collision that could have separated, and because, you know, we're talking about, these are hot bodies here. Maybe most of those minerals are liquid or even gaseous because they've just been through nuclear reactions, you know, when they got blown off the sun. So they're very, very hot. And so they're for a collision would off a drop or two, you know, or something like that. Now, here's another reason why we think maybe the moon formed that way. If you look at the moon, no matter what time of year or anything else, the same side of the moon is always facing the Earth. Always. The moon spins, but only one time in a revolution around the Earth. You never see the backside of the moon. Ever, unless you're in a spacecraft and get back there and look at it. And we have done that.
That's why the aliens are back there.
What's that?
The aliens on the dark side of the moon, huh?
Oh yeah, you've been reading, listening to those songs, haven't you? Okay. Yeah. There was actually a book by that title too, wasn't there? Yeah. Okay. And why else would it be that way unless it was once part of the Earth and is still rotating at the same
You
deal?
get into that ancient alien stuff and really the same place there.
The what?
You get into ancient aliens and
Oh,
all.
I see. They are what did it. Oh yeah.
Saying
Yeah.
that it was placed there.
I see. Okay. All right. E.T. Okay, never mind. Okay. All right. Time to move? No, okay. So that's another supporting evidence that maybe the moon did come. It's the biggest moon for any Earth, for any planet out there. Okay? And it rotates at the same place all the time. It's got to be. You would think it had to be. Something like that. And all the sampling they've taken out of it, it looks like it's the same materials too. But then that's probably true of most of the inner rocky planets, the terrestrial planets. Okay? Everybody got it? All right. Now, that was stage A, B, and C. Now we're moving to 15.4, which is ideas about the solar system. What's that? Oh, okay. The early model was that we were a geocentric setup. In other words, like teenagers, everything revolved around us. Oh no, that's okay. Now, Earth-centered. And sure, there seems to be evidence of this. The sun seemed to move around us. The stars seemed to move around us. The only problem is thinking little planets. They sort of move, and then they back up, and then they do some weird things. Everything else seemed to move around. The Earth, the moon moved around us, everything did. So that was a geo or Earth-centered model. Everything goes around the Earth. An attempt by the early Greek astronomers and philosophers to explain the observed motions of the sun, moon, and stars. The trouble is, you had to have a different system for the sun, and a different one for the moon, different ones for the stars and the planets that fit any of them. Okay. They placed the Earth at the center of the orbits of the planets. That didn't work too well. Exceptions of this model were explained by, I believe he was Egyptian, Ptolemaic system. Oh boy, he figured out some sort of mathematical way to kind of explain why those exceptions showed up. And it worked okay, but it was really awkward and bulky and things. I think it was Albert Einstein that had a famous quote back when quantum theory was just coming into play and people were thinking they were discovering all these different things, and a lot of people said, I think that's the same thing someone else discovered, you're just giving it a different name, or you're seeing something that probably isn't that. I mean, something. And he had this quote, and I think it was something like this: God is complicated, but He's not malicious. Okay. In other words, yeah, it may take some effort to separate all this, but it has to make sense. It can't have all these variations. And the trouble with this system is they just had to keep coming up with other ways to explain the variations they couldn't explain otherwise. The inconsistencies in the system grew in number and became more complicated to explain, and they said, something's wrong with this picture. Okay? Now, unfortunately, somewhere along the way here, and this sort of irritates me, somewhere along the way here, the church decided to get in on the picture, and they said, yes, we are the center of the universe. Everything revolves around us. And that made it hard to dispute, okay? Especially in Western Europe. China probably didn't have the problem with it, okay? They didn't have the same setup we did here. Now, oh, I'm sorry. So, we're about to hit on the next slide some people that started playing around with other ideas. Now, actually, one of these was that same guy we mentioned before, the 4 moons around Jupiter, named after Galileo. Galileo had read some writings from a guy named Copernicus. Anyone know what Copernicus came up with? It's going to be on the next slide. Does anyone need this one any longer? Huh? Okay.
30 more seconds.
30 more seconds.
I'm sorry.
30 more seconds.
30 more
Seconds.
seconds to what?
To keep that up there.
Oh, to keep it up there. Oh, okay. I thought you meant it was almost 5:15 already. Okay. No, please don't say that. Okay.
We got 15 now.
Anybody else need it? Another 30 seconds or so.
No, go ahead.
Go ahead. Okay. Here came the heliocentric model. How does that differ from geocentric? The sun in the center. Okay? So the idea that the Earth was revolving around the sun came from this guy named Copernicus. Now the interesting thing about Copernicus, because there's really probably 2 interesting things, there's lots of interesting things about him. One thing was he was from Poland. Now where was his church centered? Rome, the Vatican. And Poland was a long way away from the Rome. Okay? Now, here's a sort of interesting thing. Copernicus was actually a monk. He was part of the church structure, but he was also a very brilliant scientist and a monk. Yeah. Okay? And he studied this stuff, and he came up with this heliocentric model, that everything revolved around the sun. But he, being a good monk too, refused to publish it because he knew that would get him and anyone who believed it in trouble with the church. And being way out there in Poland, he could do all these studies and no one ever knew it. Okay. Well, Galileo read some about it, and Galileo, remember, had developed this telescope that was way more powerful than the original telescope. And he looked out there and he noticed several things. Jupiter was spinning. And Jupiter had moons going around Jupiter, the Galilean moons. He said, wait a minute, okay? Does that mean that we could be spinning? If we spun, that means the sun fixed in space would look like it revolved around the Earth. Hey, this makes sense. Okay? So, a couple problems with Galileo, though. Where was he from? Pisa, Italy. Pretty close to Rome. The church got wind of his writings, and if he hadn't been such a famous scientist, he'd have probably been executed. So what they did, they just put him under house arrest and made him recant everything he had written. Okay?
What was the purpose of them? Because they didn't want to.
They wanted to change their mind. Yes. Okay, excuse me just now. Do I need to turn off my recorder? Okay.
The church controlled everything back then.
You have 14 more minutes. It's her like 4 fish calling up, so she has no. There was this thing that we were supposed to fill out, and I'm like, I heard me in trouble about that. And I don't know what.
I am so sorry. I asked her if I could turn off my recorder, and she said no. I should have turned it off to keep it from dead time. Okay. All right. So, Galileo also supported this, but they put him under house arrest, so he had to recant, but he also kept another journal and said, I don't mean a word of that. And that was to be published after he was already dead. And that's actually what Copernicus did too. He ordered them not to publish his work and ordered his assistant. So as soon as he died, they published it, because they couldn't do anything to Copernicus. Okay, and that's when Galileo heard about it. So anyway, here's how the model works. Okay, if you put the sun in the center, and here is the Earth going around the sun. Mars is out here going around the sun also, but at a different rate. So, and this is what the problem was. You know where the name planet comes from? It means wanderer. Because the stars followed very certain patterns. The moon followed a very certain pattern. The sun followed a very certain pattern. The stars, they do this, and then they do this, and then they do that again. They were wanderers. They would get lost and then come back. And that's why they couldn't figure out what was going on. Well, here's why. Let's say the Earth is here, okay? This is Mars. So on this night, you look up here and there's where Mars appears to be. On this night, you look up and see Mars, and it seems to be there. On this night, you look up and see Mars. Hey, it's following a really regular pattern, right? Then you look on this night, and Mars is sped up. Hey, slow down. Hey, you were going on fine. Then on the 5th, you look here, and Mars is backed up and come back here. And then on the 6th, he's going even further back. And on the 7th, he starts going ahead again, and then gets in a regular pattern again. What is going on, Mars? If he was going around the Earth, that wouldn't make any sense at all. But going around the sun, it makes perfect sense. And that's what supported. What's that? Yeah, that's it. They got drunk and got out of. Oh, that's just okay. Now, they weaved, when they were drunk. Okay. Now, they should have gotten the ticket. Okay. All right. DUI. Okay. Now, Kepler, there were still problems because the heliocentric model placed all the planets in circles around the sun. Kepler came along and said, wait a minute, this would be even better because you still have some issues here if you make these orbits elliptical rather than circular. Now, not very elliptical, just a little bit, and that fixed everything. Except Kepler couldn't say why they would be elliptical orbits. He couldn't explain why his model worked. And I think he's the one that went to Isaac Newton and said, hey, can you tell me why? Can you give me the physics of why this works? Well, Newton couldn't by himself, so he had to develop a whole new mathematics, calculus. Then he could do it. So he not only explained the physics, he had to invent a brand new branch of mathematics. What a brain. Okay. Oh my goodness, could that be the end of the chapter? Okay. No, wait. Don't get carried away. All right. I did want to point out a few things that are not on the slide set I wish were. Okay? This shows Kepler's model. Now, this is an exaggeration, a big exaggeration. This is a circular orbit. These are elliptical orbits. The sun is at one focus, the other one, I don't know what's there or why it's there, but it is. And sometimes planets are closer to the sun, and sometimes they're further away. And what that leads to, that's his first law of planetary motion, Kepler's. He had 3. The first law states that each planet moves in an orbit that has the shape of an ellipse. Not far from being a circular sun. The sun is located at one of the foci. Okay, the second law says that the imaginary line from the sun to the planet over a given time period, the area cut out here is the same as the area here. Now that he couldn't say why, he just knew it happened. The third one was this. This is a weird one. The square of the period of the planet's motion, how long it takes to go around once, is the square of that period is proportional to the cube of the planet's semi-major axis. That's from here to here. Why in the world was that? He could not come close to that. But, I wish they showed this slide. Here's what happens when you graph Kepler's third law. You put the period here versus the distance from the sun there, and look at those planets. They fall right in line. And this takes out the distance. Remember how, yes?
So you don't make your own slides?
No, these are all manufactured. I'm not skilled enough for that kind of stuff. Okay. Yeah, I wish I were, but don't have the time either. And look at that. They're almost equally spaced. Whereas remember we say, wow, look at how far apart they are. When you put it on a log scale, they get them equally spaced. And guess what is right in here between Mars and Jupiter? The asteroid belt. That's why we suspect there may be another planet there. I mean, it would have been a planet if Jupiter hadn't been big and bossy. Okay. Now, could there be another planet out here? No reason why there isn't. But it's so far, far away. They're still looking for it. They think it's there. We just can't say why. Where or what. All right. One of the names we ran into this chapter was Kuiper. Okay? Gerard Kuiper. What time is it? I know. I see people glued to their clocks. You know, they're watching this with great intensity. I'm not worried about going over. I'm going to get told in stereo. Okay. All right. Gerard Kuiper, Gerard Peter Kuiper, was a Dutch-born U.S. astronomer, best known for a clock. So you can read this. You'll find it pretty fascinating. This cannot, if you choose to write on him, this can't be your source. So this will give you an idea, go outside the book to get your source. And then, as I say, at the end of every chapter, nothing replaces reading the text. Please read the text. When you get it done, then look at the summary. Again, it's a fairly short summary, but it does have a lot of italicized words. You'll see most of those here is the key terms here. Now, these are given alphabetically, but it gives a page where you can find them first described or talked about. But the very best thing to use for studying, I think, is the applying the concept multiple choice here, and that's 41 questions. A few fewer than last time. I think there were 50 on the last. Okay, but they have the answers here. And then there's questions for thought, 19, that's about normal. 6 for further analysis, those are pretty good to look at. Sometimes this invitation to inquiry is interesting. You might find something for a paper topic there. And then the parallel exercises, frankly, I wouldn't bother with unless you just find them interesting to do. What's that? You want a picture of them? Yeah. Oh, absolutely. Y'all can come get a picture. Anytime. You can wait till after class if you want to. You can do it now. Okay? Now, what does this mean? This means that for sure on today is Thursday. For sure on Tuesday, we will have 2 hours of class, 2 hours of lab, the lab for this chapter, and 30 minutes for the test for this chapter. Now, if you don't have your books yet and want to keep putting it off, you can. That's perfectly fine. Yeah, be sure you get the paper for the answers on it. Okay, so that's going to be allotted. Anyone who wants to go and take the test certainly can, but if you don't want to take it, you got to do that. Now, we've got how many minutes? About 25 to 30, you said?
2 minutes.
Huh? 2 minutes? Oh, you got to be kidding me. Okay. I told you I'd get a response. In stereo, okay. All right. We may not have time to start chapter 16. Is that what you're trying to tell me? Okay. All right. So, for those who do want to take the test, I'll give you the test now. For those who don't, you can go, but you need to make it up as soon as you get your books and feel comfortable in doing so.
In my lab paper, and I need to change
Sure.
one real quick.
Okay.
What time is it?
I know, I'm trying to find it. Sure you- There you go. You're hiding it. Okay. What's that? Okay, good. Thank you. I'm sorry? I can't hear you.
Is that chapter 14 or 15?
No. Today is chapter 14 test. Tuesday is chapter 15 test. We just finished chapter 15. Well, Tuesday you can take it during office hours, or you can wait until you get your book and take them all right in a row or something.
So every time we finish a chapter, we have a test.
Yes, and we have a lab. So the lab will be the There'll be 2 hours in chapter 16, 2 hours of lab for chapter 15, and then 30 minutes for test for chapter 16. Yeah.
I was just going to ask, like, what kind of questions we're going to be on test?
What kind of fun?
What kind of questions? Like,
Yeah,
is it
mostly
gonna be, like, multiple choice.
Yeah.
Right. And is it all based on what was on the slides?
Yeah, well, slides and what we talked about, that kind of stuff.
I'll take the test so that I
Okay.
can get out of the way.
What's that?
I'll go ahead and take the test
Sure.
out of the way.
Okay. Let me, are there any other questions, substantive questions I need to record? Okay. All righty. Have a good weekend.